Alright, so this is going to be the last lecture on the topology series, and we're going to be talking about metric spaces. Now, my only, I guess, hesitation with this lecture is that we're sort of going to be relying on pre-existing knowledge of the real numbers and some sort of basic facts about the real numbers, nothing too crazy and nothing that would involve topology to begin with. And the reason why I say this is sort of a problem for us is because, this is sort of supposed to be a lecture that goes in order, and since the next thing we're going to be covering is real analysis, we technically haven't introduced the real numbers formally, but this lecture fits in nicely, I think. I could have saved it, but I'd rather put it in here so we can connect it to some of these topological properties, and we can talk about metric spaces in general before we talk about just the real number line and Euclidean spaces in general. So without further ado, I guess, we are going to be defining what a metric is. A metric is a function which takes a Cartesian product of a non-empty set with itself and sends it to the real numbers. And it satisfies a couple of properties. The first property is that the value of the metric is always going to be greater than or equal to 0, right? So you can't have a negative value for your metric. The next condition is that this metric is only going to be equal to 0. It's equal to 0 if and only if x equals y. So essentially saying that if the a metric is going to be sort of a generalization of distance, right? So I'm going to be using the word distance as sort of like a connection, like sort of a vague connection to what we already think of. So if the distance between x and y is 0, then x and y are the same point. The third property is that the metric is symmetric. Get it? Symmetric. And that d of xy equals d of yx, right? It doesn't matter the order that we have the input variables in. And the final property, which is the most sort of convoluted, and usually when you're trying to prove that a function is a metric, this is the hardest to prove. It usually involves a lot of casework and stuff like that, is that essentially in non-rigorous words, it says that the distance between 2 points is always going to be better than, or it can't be greater than the distance going to some other point and then back. So if you have some third point in the middle, you will never achieve a smaller value of the metric. And so this is called the triangle inequality. And this is sort of the most important aspect of a metric, in that it sort of gives you that oomph, right? It's like all of these other properties are sort of not that strong, right? But the triangle inequality is very strong, and we can use it to do a lot of a lot of technical stuff, right? A lot of proofs in real analysis essentially boil down to just using the triangle inequality at the right point. And so if x has this metric D, then we call x and D a metric space. And so as an example, right, and again, we haven't technically constructed the real numbers, but the real numbers along with the absolute value function is a metric space, and the absolute value is defined as x when x is greater than or equal to 0, and negative x when x is less than 0. So you can see right away that it's always positive. It's only going to be 0 when x is 0. Or technically the metric here would be so d of xy technically is the absolute value of x minus y. I should specify. So this is going to respect the symmetry property, and then again, to prove the triangle inequality is a bit of casework. Basically, between how the points x, y, and z are related to each other on the real number line. And so the reason I wanted to formally introduce this absolute value function is that something you can prove, which is basically like a negative version of the triangle inequality, says that if you take the difference between two values of the metric, and the absolute value of that is always going to be less than or equal to the distance between, or the value of the metric between. So it's like the triangle inequality where you have this intermediate point y, but here you're subtracting and you get something on the left-hand side. And the proof of this essentially just uses the triangle inequality twice, right? You basically take care of two different cases where this absolute value, what's inside the absolute value rather, is positive or negative, and you get two different cases that are both equivalent to the normal triangle inequality. So now we want to investigate, okay, why are we talking about this topologically, right? Where's the topology? Our metric is going to induce a basis for a topology on X. And so let's see why that is. What we're going to do is define these sets B sub R of P, where P is an element of X, R is some real number which is greater than 0. This is going to be defined as the set of elements X such that the distance between X and P is less than R. So these are essentially just balls, right? So and again, we haven't really dealt with the real plane, but if we want to take the real plane as an example, then these are sort of, you have your point P and your radius R, and you have everything shaded in except this dotted outline, because the dotted outline is where the distance between X and P is equal to R, and that's going to be like the boundary of your set, right? So this collection of B sub R of P, where P is an element of X and R is greater than 0, is going to be a basis for a topology on X. And the proof of this, right, you have to show that this collection satisfies the two properties for a basis. The proof of this is essentially like that if you have some set, then you can use the triangle inequality to construct some open set which is contained, or not some open set, but some ball which is contained in here, right? And then similarly, if you have two elements of the basis that intersect, and you have some point in the middle, you can also use the triangle inequality to construct a third basis element which is contained in here. And so these are the two properties that you need for a basis, and so these proofs essentially just use the triangle inequality, which I will write as a triangle dash inequality because I'm lazy. But yeah. So the first big thing that we can sort of say about these metric spaces is that in relation to the separation properties that we talked about last time, a metric space is T2, or Hausdorff. And the proof of this is pretty simple. If you have two distinct points, then you have a distance between them, and therefore you can construct these open balls using a radius of the distance divided by 2, right? So this R is going to be half the distance between P and Q, and so these open sets are going to be disjoint. Like they just barely meet, but since they're open, they don't intersect. And therefore you can always separate 2 points. The next thing, which is pretty interesting, if you have two metric spaces, so let's say x1, d1, and x2, d2, and f is a function from x1 to x2, then f is continuous. Remember, continuity is something that we defined in general on a topology. But here we can say an equivalent definition for continuity using the metrics d1 and d2, which says that for all p and x and epsilon greater than 0, there exists a delta greater than 0 such that Q, if Q is in the ball of radius delta around P, in other words, if the distance between Q and P is less than delta, then F of Q is going to be in the ball of radius epsilon around F of P. In other words, the distance between these two is less than epsilon. And so if this looks familiar to you, this is the definition of continuity learned in a calculus class. And this is because R is a metric space. Right? And so this is an important theorem that you should go through. So I'll just give myself a little bit of room over to the side here. The next thing we can say which is pretty useful, is that if f and g are continuous from a metric space X to the real numbers, then f plus g, c times f, and f times g, and so c is a real number here, are these are all continuous. And the proof of this essentially just uses this new epsilon delta formulation. The proofs are a little tricky, or at least these two aren't as tricky, but f times g is a little trickier. Oh crap. But yeah, that's something you can prove, and you should prove as an exercise. Alright. Now we depart into some more topological aspects of these metric spaces. So let's let A be a subset of X, and X just be a point. We can define the distance from X to A to be the infimum, which I'm going to define in just a second, of all the distances d of xy, where y is element of A. So what this definition is saying, right? This inf is known as the greatest lower bound. And so again, this is a real analysis thing that we're sort of jumping ahead, but I can just define it. This says, and I'm going to, actually I won't. This says, if y is in A, then the distance between x and y is always going to be greater than or equal to the distance between x and A. And if m is if m is greater than the distance between x and A, there is some y in A such that the distance between x and y is less than m. So these two things put together essentially say that d of xa is sort of the precise distance between x and A, right? It's always going to be less than or equal to any distance between x and a point in A, but if anything is bigger than it, then there is something in y which is closer than that distance. And so again, this is sort of something that you might have seen before, but if not, I'm defining it just in case. So now we can define some properties of this new function. Let's see. So the first thing is that d of xa is 0 if and only if, or this is equivalent to saying x is in the closure of A. And so notice how this is different than what one might expect, because remember, the distance between 2 points is 0 if and only if they're the same. So you might expect that this distance is 0 if and only if x is in A, not the closure of A. But the reason we can allow the closure to cover everything is that if x is in the boundary, then any open set, or really any neighborhood, I should say, of X intersects A. In particular, any ball of radius R intersects A. So you can, this is essentially saying if R is greater than 0, there is some Y in A such that d of xy is greater than R, or less than R, I should say, sorry. Which essentially this just satisfies, if you put 0 for the d of xa in this statement, that just satisfies this condition, right? So that's why we can include the boundary of A. The next thing, and this one is a bit tricky to prove, that is the distance between x and a minus the distance between y and a. If we subtract and take an absolute value, this is going to be less than or equal to the distance between x and y. And to be honest, when I was taking my notes for this lecture, I blanked on how to prove this, but I proved it in the past, so I'm confident you can do it as well. And from this result, we get that the function f of x, which is equal to the distance from x to a, is continuous. Essentially just using that epsilon delta definition, since we can use, we can prove continuity using distances. This also allows us to prove something a lot stronger than what we showed before, right? Remember, we showed before that a metric space is always T2, or Hausdorff, and that proof was really, really simple, right? It just came from the basis for the topology that we had. However, using this new machinery, you can prove that a metric space is T4, right? So it's normal, and essentially, right, you would have two closed sets, A and B, and you would want to use this inequality here for both A and B to construct an open set, or to construct two open sets, U and V, right? And another thing that will be useful, since A and B are closed, A is going to be equal to its closure, so the distance between x and A is 0 if and only if x is an A in this specific case, and the same goes for B, since they're both closed. So that's sort of like a little hint towards how that would be proved. And the last result is that a compact subset, or I guess first I should define a subset of a metric space, so X with a metric D, is bounded if there is some m greater than 0, such that for all x, y, so I should call this subset A, for all x, y, and A, the distance between x and y is less than m. So for instance, how should I say this? A ball, right? If we consider the ball B sub r of p is bounded. And we can prove this by using m equals 2r, right? And that's called the diameter, because if I take 2 points, x and y, I essentially just you essentially just use the triangle inequality, because how should I say this? The distance between x and y is less than or equal to the distance from x to p plus the distance from x to y, or sorry, from y to p. And both of these distances are less than r, because these x and y are in the ball, so these are both less than 2r. So the distance between x and y is always less than 2r. Like that. So the last result is that a compact subset A of a metric space, xd, is bounded. And the proof of this is pretty cool. You can essentially just take an open cover, b sub n of x, where x, you could say x really can be, or really just any point, and n are all the natural numbers, right? So what this means is that this is an open cover, because you're essentially just saying that, and this actually has to do with another thing from real analysis, which is called the Archimedean principle. Which is that if y is an A, the distance between x and y has to always be less than n for some n in the natural numbers, right? In other words, you can always find some natural number which is bigger than a real number. So this is called the Archimedean principle of the real numbers. So this shows that B is in this ball, right? And therefore this constitutes an open cover, but then you can find a finite subcover, and if you have a finite subcover and all of the open sets are essentially just indexed by natural numbers, so if you have a finite set of natural numbers, you can find the biggest one, and then that constitutes your value of big M, and so that shows that the set is bounded. And so that concludes the topology series. And so even though we sort of skipped ahead and used a little bit of real analysis already, I think it motivates, I think this section sort of motivates what's to come for analysis, which is, you know, the use of the triangle inequality, and some other definitions like the infimum and the Archimedean principle, and all those things we'll take care of technically in the next series. So that's it. Do you have any questions?
No, sir.
All right, that's it.